Hello and welcome back. Today I want to continue working on the topic of common mode and differential mode noise separation. Last time, more than a year ago, I looked at how on a two-line system the noise can be separated by adding and subtracting the information present on the two lines, as well as a practical implementation of this using an oscilloscope. And today I want to look at how the same function can be implemented using a more practical passive circuit. Something that can be used together with a spectrum analyzer. So if you're curious about that and much more, then keep watching. First, let's remember a few things about how noise can exit a circuit. Now, when talking about conducted emissions, you have two types of noise that need to be treated differently: common mode noise and differential mode noise. Now we can create a model of the two types of noise source in something like this. So differential mode noise is the type of noise that will come out through one of the supply lines and go back through the other line. So differential mode noise completely closes back through the supply lines themselves. Common mode noise, on the other hand, goes out through one or both lines at the same time and closes back always through a common ground plane. So common mode noise usually is capacitively coupled at both ends, so on the one side at your circuit, on the other side at the measurement setup. And because of the way in which the two currents pass through the circuit, they need to be filtered differently. Now, it's important to mention that when you're performing your regular conducted emissions measurements, you will be using something like an LISN, a line impedance stabilization network. And what makes this thing special, or rather limited, is that this circuit will be measuring the absolute noise present on each of the lines separately. So that device will not tell you what way the currents are going, obviously, and it will not be able to tell you whether you're measuring a differential mode noise or a common mode noise. It will only tell you that there is noise there. So the first thing to do if you want to make an efficient filter for your specific noise type and specific problem area is to know exactly what kind of noise you're trying to filter out, since the two types of noise will have two different filtering requirements. Now, before attempting to separate anything, it's important to have a clearly defined noise source. So today I will be working with a circuit similar to that I've built in the previous video, with a few minor modifications. So this is the circuit that I will be using. It has two BNC connectors through which I'm injecting the two types of noise, and then it has two output pins, so two connector pins through which the noise is being output. Now, the common mode noise gets capacitively coupled between both of the lines and ground, whereas the differential mode noise gets magnetically coupled through a transformer directly in between the lines. So the differential mode noise closes in between the two pins, whereas the common mode noise closes in between the pins and the ground. Now, from a layout point of view, nothing special was really done here. So I have the two BNC connectors on top, the two connectors on the bottom, transformer in the middle, and then the various passives. So there might be better ways of implementing this, but this is how I built it. And I will be using this thing to create the two types of noise, and then use some sort of circuit to separate the two noise sources. Or at least to try to do that. First, before trying to separate our noise sources, let's first see how they look on a normal LISN. So for that I prepared the setup right here. I have my spectrum analyzer, I have my noise mixer, which is connected to two channels of a signal generator, and this is connected to an LISN. So if I connect the LISN to the spectrum analyzer, we can see two spikes appearing, one at 400 kHz, one at 500. Now if I swap around the channels of the LISN, so measuring on the other line, we basically see the exact same thing. So just by looking at the noise measurement using the standard LISN, we cannot tell the difference between the two spikes to say which is common mode noise and which is differential mode. And also we can't even tell if we even have both types of noise. We only know that there is noise on the lines. Now, last time we've seen that the separation process can be performed using an oscilloscope and its mathematics functions. So addition and subtraction on two input channels. But that method won't really work with something like a spectrum analyzer that has a single input. So we need some sort of circuit to perform the addition or subtraction operations for us. Now, while preparing for this video, I came across this research paper. So this is on the analysis and practical relevance of common mode, differential mode, EMI noise separator characteristics. And here a single phase noise source is analyzed. So from a common mode and differential mode point of view, all of the mathematics behind it. So this paper goes into quite a bit of detail. It's quite good. I highly recommend it. And finally, they propose the schematic for an active separator. So a separator which, well, works with operational amplifiers to perform the two operations. So on the one side, summing the two signals to provide the common mode noise, and on the other side, subtracting one signal from the other to provide the differential mode noise. And finally, the paper discusses the performance obtained with this circuit. So you can check that out if you're curious. Now, initially, I wanted to build a circuit similar to this, but then I decided to do something a bit more simple and basic. The thing is that in real life, you don't really need a perfectly balanced circuit with extreme precision and very good separation properties. Most of the noise you will end up having will be either of one type of noise or the other. You only need to know which type it is. Measuring it accurately will be done using the LISN anyway. So, is there a more basic way of building such a circuit? I then came across this other paper. So this one's entitled Diagnosis of Conducted Interference with Discrimination Network. So this is an older paper and they discuss the same topic, so of common mode and differential mode noise, how it can be separated. And the network that is proposed here to separate the two noises is this thing. So this is a very basic setup. It contains two transformers, and based on how the second transformer is connected to the input, the noise on the secondary sides ends up being added together to provide only common mode noise, or subtracted one from the other to provide only differential mode noise. And from a complexity point of view, well, you can't really get more simple than this. I mean, this only uses two transformers and two switches. Now, there are a few important things to observe here. First of all, since the circuit only uses transformers, it's a passive circuit. So no need for external power supplies. Secondly, since transformers are involved, you can build the transformers any way you like. So in theory at least, you can get this thing to work with any frequencies or any bandwidth. And at the same time, you can work with any voltages. So small voltages, large voltages, doesn't really matter. You're not limited like with the op-amp circuit, where the exact choice of op-amp has a great influence of how well and over what conditions the circuit works. So today, I will be trying to build something like this thing. Now, the principle on which the circuit in the paper works can be illustrated using the following circuit. So if we have two transformers with the secondaries interconnected, and we apply a certain current on the first transformer and a certain current on the second transformer, based on the direction of the currents in the second transformer, the two currents in the secondary side will either end up adding up or being subtracted one from the other. So based on the direction in which the currents in the secondary are going, in reference to the first. So if you have two equal signals but of opposing phase, so for example with differential mode current, then in the secondary side the two currents will cancel out and you will end up left with nothing. Whereas if the currents are going the same way through both of the inductors, then on the secondary side they will add up and you will have double the initial current. So the sum of the two currents on each of the two lines. Now, the only problem with this circuit is that it requires two separate transformers to operate. Let's see if we can't make this a bit simpler. Now, alternatively, we can perform the operations with the magnetic fields of the initial two inductors. So if we place both of the two initial inductors onto the same magnetic core, based on the direction in which the currents are generating the fields in the magnetic core, we can perform the addition and subtraction operations. So if current is going one way through the first coil and the same way through the second coil, so with blue and orange, the two magnetic fields will be going into the same direction, and then your secondary side will see the sum of the two magnetic fields. On the other hand, if one coil has current going one way and the other coil has current going the other way, so two opposing magnetic fields are generated, then the secondary coil will see the sum of the two fields which are opposing, so they will cancel out. Therefore, the secondary will see nothing. So we can perform the same addition and subtraction operations by using a single transformer with 3 coils. And this is the type of circuit that I will be trying to implement today. So, to show you what I planned for today, I prepared this LT-Spice simulation. So what I have here is 2 circuits. Let's take them one by one. So I have my noise source. It contains a differential mode signal between the 2 supply lines and the common mode signal in reference to ground. Then on the other side we have a power supply, which is a purely passive circuit at the moment. So our noise source is the circuit that's being supplied by the power supply. It's not really the power supply, that's why that one is a passive circuit. But anyway, the circuit of interest is this thing in the middle. So I built this transformer with 4 inductors. One of them is connected to the spectrum analyzer. So this is the 50 ohms. And then another inductor is directly connected on one of the lines. And the other 2 inductors are supplied either one or the other based on what type of noise we're trying to extract. So for common mode noise, we're supplying L2. For differential mode noise, we're supplying L3. Now, other than the transformer, I also added some capacitors. This will also help with the separation process. So first of all, when we're measuring common mode noise, I already have a capacitor to short circuit any differential mode noise right at the beginning. But also we have the same thing at the end, so it's C6. And we also have C7 and C8, which pull the 2 supply lines to ground. And then in my second circuit, we have the exact same circuit, exact same noise source, the only difference being that this time the differential mode signal is being supplied. So let's run this thing, see what comes out. So we can look at what's on the differential mode output and also on the common mode output. And to get a clear picture of what's going on, I will be viewing the measurements as an FFT trace. So I separated the 2 graphs into 2 plot planes, and we can see that with our common mode output we only see one spike, and then with the differential mode output we only see the other spike. So by using the separator, we should be able to separate the 2 different types of noise quite well. Well, at least in the simulation. Let's see how well this can work with the practical implementation. Now, from a schematic point of view, I have basically the same thing as we saw with the simulation. I have my input pins, so this is where the power supply would go. And then the output pins are where the tested unit goes, so the noise source is on the right side. I have these connectors. Then I have my 4-winding transformer. One of the windings gets connected to a BNC connector, which goes to the spectrum analyzer. And then the 3 windings, one of them is directly connected between input and output, and the other 2 you can select between them based on which pin you're inputting your noise into, so the differential mode or the common mode. And then, other than the transformer, I have a bunch of 100 nanofarad capacitors. Now, from a layout point of view, again, nothing special. I'm using a 2-layer board. I have my DUT side connectors on the left side, my supply side connectors on the right, I have a BNC connector and then the transformer, and then everything is just interconnected. So I didn't really use any special layout rules, I just, well, applied it like this. Now, to build this thing, I used a ferrite ring core, and each of the windings is a single turn going through the core, and I saw this trick somewhere to create a wideband transformer by using different cores in parallel. And I tried to implement that. So the green core is from an old 10 millihenry common mode choke, so it has really high permeability, but because of that, this core won't really work well at high frequencies. So for that, I added the yellow core, which was from a 10 microhenry inductor, so it has much lower permeability, and this core should step in once the frequency increases. So now, let's see how this thing actually works. And to do that, I prepared a setup with my spectrum analyzer, in which I saved our initial measurement. So these spikes in pink are what our initial LISN measurement gave us. And I have the same noise source connected to the signal generator. And now if we connect it to our separator board, first of all, if we insert the signal into our differential mode input, we can see that our right spike is almost exactly the same as what we measured with our LISN. So we can clearly see our differential mode noise being unaffected by the separator, but our common mode noise is about 40 decibels lower than our initial measurement. So this is a 10 decibel per division scale. And now if I swap around the inputs, so plug my input into the common mode signal, we can see our left spike even larger than before, so it's almost 10 decibels larger, but our differential mode spike is more than 30 decibels lower. So by using the separator, we can clearly make a difference between the two spikes and the initial LISN measurement. So we can clearly extract what is common mode, what is differential mode. Now, just to see how well this device works over a wider frequency range, I made the exact setup as before, but looking at two spikes, one at 19 MHz, one at 20 MHz. So I already prepared the measurement with the LISN, in which I have the two measurements in pink, so this is the unseparated measurement. And now if we connect our separator, first of all on the common mode input, we can see our common mode spike slightly attenuated, but we have a far greater attenuation on our differential mode spike. And if I swap around the two inputs, we can see the story changing. So our common mode spike has a larger attenuation, our differential mode spike has a smaller attenuation. Now, it's not as great as we had with our low frequency spikes, but part of the issue here can be with the noise mixer itself. So it doesn't work that great at higher frequencies. But finally, let's look at a more interesting measurement. How would the noise from an actual device get separated? And for that, I'll try to separate the noise coming from my old cell phone. So it's all broken up and busted and so on, but you can still charge it. So I'll measure the noise coming into the charging port and then see how it looks with the separator. So first of all, to get a baseline, I've connected the cell phone through the USB charging port to the LISN, which then goes to a 5-volt supply. So right now the cell phone is charging, it's pulling around 500 milliamps of current, and we can see our noise emission spectrum. So the plot is going from 100 kHz to 80 MHz, so just below the FM band, and we can see quite a lot of noise here below 1 MHz, then we see a clear spike at 3 MHz, and then a bunch of harmonics of this 3 MHz spike. So this is probably some sort of switching converter, and we're seeing its harmonics. So now I'll freeze it, and then I'll take out the separator to see what part of this noise is what kind. So first of all, I set it into the differential mode measurement. So we see most of our initial spike is differential mode, so is our 3 MHz spike, and then the differential mode noise starts to die out. So this high frequency stuff seems to have only a partial differential mode content. Now if I switch around to common mode, so again the phone is getting charged, we can see that our spikes and the harmonics mostly died out. So they're not common mode, they're differential mode, as we've seen with our previous measurement. We can only see a bit of common mode here at the end, and part of the initial noise is common mode, part of it is differential mode. So most likely this spike is coming from the power supply from which I'm supplying everything, so that's why it's common mode. But regardless, in such a complex system, having this sort of separator will be quite useful to be able to determine what kind of filter is needed. So how do you make a filter specifically for common mode or differential mode noise? Well, that's a topic for a different time. For now, hope you got some useful information out of this. Leave your thoughts in the comments. Thank you for watching. Make sure to subscribe to be up to date with all my latest videos, and see you next time. Bye bye.